So this is hybrid, voltage and current mode. So I have decoupled both voltage path and current path. So my voltage path can keep regulating the V out and current path will supply me the ripple. Okay.
This RF should be less.
Which RF?
The feedback resistance.
I mean less in the sense, if you make too small, then what would happen? This, it will suppress the ripple at Vf. Huh? So you have to make sure that don't keep, so usually it's order of 50 to 100 kilohertz, sorry kilo ohms. Okay. So it all depends on the, I mean what CR you are having, based on that you choose RF. If you think like 10K or 20K will be sufficient, then you can use that, that is not a problem. So controlling so now if you remember these two expressions, so this is current mode, this is voltage mode. So what are the different ways we can control the switching frequency here? So I think this was delta VH, huh? Correct? Delta VH by RESR was the delta L. So let me fix that also. Okay. Tell me what are the different ways to control the frequency in two cases? Inductor? Inductor is not in your control. Huh? Once you have fixed the inductor, duty cycle is also you cannot change.
Delta VH.
So delta VH and RC CC. Here only delta VH. Okay. RESR you cannot change dynamically, L you cannot change dynamically. So the only component you have to control the frequency in voltage mode is delta VH, and we saw that how much could be the frequency variation. I mean at 50% duty cycle, if you fix 1 megahertz, and how much was that? So from 0 to 5 you remember we are going to 0.1, so 2.5 times change, it's more than 2x change. Huh? And once you consider the changes in L and RESR, it may be 4-5x. So 10 millivolt is the ripple. If you want to reduce to let us say 10 times, your hysteretic window may required may be 1 millivolt. Okay, 1 millivolt means like you have a comparator, offset, noise, everything will kill it actually. It will not work at all at 1 millivolt. So very difficult. Very difficult to control FSW due to small delta. Okay. fix delta VH and FSW can be easily controlled by RC or CC. So, usually we fix CC and change the RC, because we do not want to usually, I mean, varying the cap with the switches is not a good idea, because it introduces RESR and all those. So, it degrades the quality of the cap, and that means you may require a very big switches. But you know, these resistors are order of kilo ohm, you can change with a very small switch. So, that is why we prefer. So, this is preferred method. Okay. So, what does it mean? Why do we want to control the frequency? So, we know it is varying. Okay. So, now we have a way where we can operate it at a fixed frequency. So, if I want to operate at 1 megahertz, so let us say at 50% duty cycle, I fixed at 1 megahertz. When it is varying, I can always fix it at 1 megahertz by simply controlling the RC. So, what RC will do? It will change the slope of your ripple. I mean, it is similar to your current mode. In the current mode, when the slope is changing, so it will try to change the duty cycle. Okay, but only frequency is changing, but duty cycle is not, do not want to change. So, your feedback will force the, if let us say on time is changed, feedback will force off time also to change, because we want to keep the same duty cycle. So, how do we control the switching frequency here? What do we need to detect? And so, you need some control, some feedback control to control the frequency. So, this is your R C. I am only drawing that portion. RDCR, this is your VSW, RC, CC, this is your VO. So, first thing I need a reference clock. If I want to operate at 1 megahertz, then it should be 1 megahertz. So, I will call it CLK ref. FLL is nothing but frequency locking loop, and it generates a, let us say, code, digital code of D n minus 1 is to 0. It is n bit code, and it goes back here and controls your resistor, and this is nothing but RDAC, resistive DAC, and this needs to be compared with VPW. This is frequency locking loop. So, what it does basically, it forces FREF or FSW equal to FREF. So, if this is FSW and this is FREF. So, if I want 1 megahertz, I will make FREF 1 megahertz, and this will generate a code which will fix the RC in such a way that VPWM is 1 megahertz operating at, or FSW is 1 megahertz. That is what it does. So, you need another loop for this. So, then you build a, and this is nothing but fixed frequency. Static converter. And if you look at the chapter which I chapter 4th of my thesis, where I have expression for that basically Ts by 2 Rc should be. So, the same chapter talks about this also, how you implement FLL and everything is there. And once you take the PLL course, you will know how to implement this. It is all digital actually, very simple. You just need few flip flops and you are done. Okay. So, if I remove this inductor, so in terms of this current loop, let us put this directly and remove this also. So, in terms of frequency, there is no change as such, because your RC time constant is defining the frequency, correct, and you are only looking at a ripple component. So, let us say forget about the regulation, then in terms of frequency there is no difference between this and whether you have the inductor or not, or whether you have a feedback loop, until unless your component which is coming from the output is significant compared to your this ripple component, only then it will start affecting the frequency. Otherwise, if you consider that ripple in the V out in this case is much smaller, so the ripple at the V out is much smaller compared to the delta VH actually, which is your peak to peak ripple. Your ripple is limited within that window, then it should not affect your frequency. So, frequency will only be defined by your hysteretic window and RC time constant. So, if I remove everything and keep only this comparator and RC component, and you can think about this is only buffer, the gate driver is acting only as a buffer. So, what exactly this is actually? Not filter, but this is acting like an oscillator. If you see, if I remove this whole thing and this is as good, you consider this as good as ground, because V out is DC, then this will act as an oscillator. Do you guys remember the RAM generator, triangular RAM generator? We had a charging and discharging current. So, it is similar, instead of that you have RC here, that is the only difference. And as long as your RC time constant is much large compared to your time period, then you will get a same behavior as your current charging and discharging that capacitor. Okay. So, this is acting as an RC oscillator, nothing else. So, what if I have a delay TD? So, what if this comparator has a delay of TD? What would happen? So, one is the ripple, what about the time period? It will remain same, it will change or increase, decrease? It will increase, So, see if this is my delta VH. And same thing you can do. This is TD. Here also you have TD. Okay. What does it mean? When your comparator trips, that VPWM will look slightly delayed. So, let us say a comparator goes from high to low. So, the state will not change instantaneously, but after TD delay. Same thing happens when it goes from high to low, which means until that time your VC will keep charging or discharging. So, you will get extra peak and valley, correct, which means, so what if the slopes are same? If slopes are same, then this delta VH on the higher side and lower side will remain same. So, average will not change. But let us say, which means the slope can be same only if you have 50% duty cycle. If it is a non 50% duty cycle, then one side will be more than the other side, okay, which means at lower duty cycle your rise time is faster, okay, it will be rising faster. In that case, what would happen here? It will peak more and valley will be less. So, your average voltage will be looking at slightly higher side. If you are operating at a higher duty cycle, then it will be discharging faster, correct, and then your valley will be more compared to your peak and average will be on the lower side. So, there will be an error introduced due to this delay at non 50% duty cycle and your frequency will also change. So, if this delay is very small fraction of your let us say time period, then it may not matter, but if it is a large fraction, let us say you are looking at a 10 nanosecond, you are operating 10 nanosecond delay and you are operating at 1 megahertz. So, it is a 1% of that, but think about if you are operating a 10% duty cycle, which is 100 nanosecond on time, and 10 nanosecond of that is 10% actually. So, that will look like huge in that case. So, you can derive the expression, all you need to do, just in the delta VH, instead of delta VH, you have to take a component of this, and this amplitude you can calculate. You already know the slope. So, how did you calculate the amplitude? V in minus V out over RC multiplied by your on time D times TSW. Now, this extra will come on TD. So, same slope multiplied by TD, that will give you that extra component. So, you have to add that portion. So, in that total time basically TD will also get added, and when you calculate the switching frequency, you will see this TD will affect your switching frequency. Okay, so I will just show you guys the final expression. So, this is for voltage mode. You remember in the denominator you have delta VHL. Now, with the TD, this extra component will come, and okay, this is what I wanted to show. So, this is happening due to delay, and you can see this is non 50% duty cycle and this is much larger compared to this. So, average will be shifted down. So, if you do the same thing at lower duty cycle, I mean much lower than 50%, then you will see this component will be more compared to this, and this is already given in my thesis actually. If you look at the same chapter, this is given, and how you calculate those frequency and everything is given. So, final expression with that RC will be this, with the L it will be that previous one, this one, and this will be with the RC. So, V in into TD, this will be the extra component which will be added, which means your switching frequency is now inversely proportional to TD, which is expected. The delay is more, frequency will reduce. So, which means there is another variable which you can control to control the frequency. If I change the delay, now I can control the frequency. But the problem is, we already discussed, large delay means this error going to introduce. So, this is not a preferred way of doing that. You may find some paper which are showing like you controlling the frequency of hysteretic converter with delay, actually TD, and people have done in the past. You can see this one. So, they have a delay line and with the PLL, just like FLL we had, and they are controlling the delay. But the problem is, larger delay means you are degrading the transient response, and so frequency you can still control with TD, but the problem is the large delay means transient response. So, that is a bigger problem. Other problem is this accuracy is going to be affected. So, that is why that is not a preferred way of doing that. So, we always try to minimize this TD and control this frequency only using this RFCF. Okay. So, this we already talked about, your error I out into RL. So, this is what I was talking about yesterday. You have two loops. One is your, now you have 3 loops actually. One is your voltage loop. So, this is your ramp which is generated from this RC, correct, and then this will decouple your DC component and only pass the AC, and this RC will in the feedback will couple this. So, your VFB will have a AC component, and DC component of this VFB will be driven by your output, okay, beta times output. So, this is your basically voltage regulation, and AC component is controlling your, or ripple component controlling your frequency, and this we know this component we can change by simply changing the RC time constant. So, this FLL or frequency locking loop is controlling this R. Okay. So, all you need a PFD is built using a simple flip flop. So, that is, and accumulator is nothing, you already know, we talked about accumulator in digital LDOs. So, it is the same thing, it is like a up down counter. Okay. So, depending upon whether frequency is low or high, it will keep counting up or down, and it will increase or decrease this resistor unless these two frequencies are locked the same value.